All right, so welcome to lecture one of the 5828 Foundations of Software Engineering. My name is Ken Anderson, and we're going to be going through graduate level introduction of software engineering concepts, tools, techniques throughout this semester. So one way I love this quote by David Wheeler. It's true about almost everything in computer science. All problems in computer science can be solved by another level of indirection. What do you think David means when he says this?
If you go up a level, make it more abstract, it simplifies things and makes the problem.
Yes, exactly. So he's focusing in on something what actually I'll return to later in the lecture called abstraction, which is you can often be at one level trying to solve a particular problem and be at one level of detail, and things are really kind of murky and or complex or complicated. But you realize you're starting to get a handle on what you need to do at this level, and that people above you at the next level up don't need to know all of this. And so you can simplify it for them by putting a layer of abstraction on it that says, hey, it's complicated down here, but I know all you need to do is open a file and save the contents of memory to disk. So what I want you to do is call open, and then I want you to call the put line or write, then I want you to call save, and then I want you to call close. So suddenly the person at the next level of abstraction has a much simpler view of the problem. I know what to do. I open, then I write, and then I save, and then I close, and I'm done. And down at the layer of abstraction, beyond that layer of abstraction, you are the one who's taking care of, okay, where's the disk drive, where's the disk head, let's get it to the right place, let's have it write data, let's confirm the data's there, and we can then, they want us to close it, I can let the disk head go someplace else, I don't really care anymore. At that level of detail, there's a whole bunch of, at that level of abstraction, there's a whole bunch of details that need to be managed, but by putting a layer of indirection, you can make it much simpler at the next level up. And so, of course, the assertion here is that that's how we solve all problems in computer science is, don't worry about these details, here's your abstraction, right? And you get to play with this abstraction, and I'll be behind making sure that everything else works as we need to. Now, here's a great tweet I saw the other day. It actually came out in 2013, but I just encountered it recently. Always wanted to travel back in time to try fighting a younger version of yourself? Software development is the career for you. So what lesson, what kind of thing is he getting at here with this tweet? What?
Record different versions of your development.
You are, I'm sorry, recording? I just didn't quite hear you.
I mean, to record every version.
Yes. So, there's these. I guess one thing you could say is that code can live a long time. And so it could be nice and clear for you today. You're writing it. You finally get it to the point where it works. And then 6 months later, you go, I think I worked on something similar to this. Now I've got kind of the same problem. So let's go back and look at this code. Oh my God, who wrote this? It's horrible. I didn't write a README. There's no way for me to. I don't know where I jumped in. What does this thing do? Why is this flag ignored? Right. So sometimes your own worst enemy is you 6 months previous not documenting or not being clear or being really fast or loose with your abstraction and not leaving it in a good thing. So here, this is kind of a comment that says code lives a long time, and we have to be conscious of the fact that we might live with our own code for a long time, and so anything we can do to improve our own code now is going to help our future self down the line. And likewise, any code that you encounter in your career, if you join a new software organization and they say, you're going to be helping us with some maintenance tasks, so go take a look at this repo. All that code written by someone way in the past could be present today in the company, but may also be like you, have forgotten what it was like to write that code that was a year or so old. My own brother actually works for Raytheon out in California. And I remember when I was growing up, was back in the days of Ronald Reagan, and he had this notion that we were going to develop a missile shield, despite the fact that most experts thought that missile shields were pretty much impossible. So companies got together and started working on this, and I remember at the time that in the popular press, one of the projects was known as Project Brilliant Eyes. And so this was all in the early 1980s, right? So somewhere in the early 80s. for that. And just a couple of years ago, so it must have been, must actually be more than 8 now, because it was during the last Bush's presidency. At some point during his final couple of years, he mentioned once again the notion of a missile shield popped up into the popular press and was being discussed again. So my brother gives me a call and says, "You'll never guess what I'm looking at." And I said, "It's true, I won't. Well, what are you looking at?" And he goes, "I'm looking at source code that has a header that was written in the early 80s, and it says Project Brilliant Eyes." Right? So the code had just been archived. Whatever they had worked on back in the 80s had just been archived. It got back into the press. It looked like the government might go in that direction. It was unpacked, and he had to go take a look at it and try to figure out. So that's code there that was just archived and hung around for 30 years, if you think about it. And still something that the company wanted to retain and possibly make use of going forward. So code lives a very, very long time. So this I liked. Elon Musk is the CEO of both Tesla, and which is the electric car company, and SpaceX, which is trying to privatize space travel. And this was a tweet he pushed out about work they're doing on Tesla recently. It was about 12 days ago, I think. Or 25 days ago. Almost ready to release highway auto steer and parallel auto park software update. Right, so somewhere out there, there's a team who is, their goal is to allow a car to park itself. Right, so I get up near close to where I want to be, and you just push a button, and it'll park itself. And I think this was parallel park, right, which is the hardest thing to do in cars. I've seen people try 17 times to get into a spot and then eventually fail, right? So they're trying to solve that so they can sell more cars down the line. And also highway auto steer, right? So most of the time you're on a highway, especially if you're traveling through places like Wyoming or Kansas, the highway's a straight line. Do I really need to keep my hands on the wheel and keep it straight? Probably not. I think it looks like you could do it. And if it's a nice gentle curve, software should be able to handle all of that. So he's got teams at Tesla that are working on exactly this. This is their feature set that they're trying to thing. So the next tweet is, why can't they release it? Well, we can't release it because the final corner case is dealing with low contrast lane markings, faded white on gray concrete, while driving into the sun at dusk. Right? So this is the corner case. This is one of the cases. The corner case means it's a weird pathological situation. It doesn't happen very often, but when it does, we'll fail. Right? So here's this corner case that they're working on. Someone is trying to get it so that the auto steer still works correctly when it can't see the lane, because the sun's coming straight at the camera, and the line marker itself is faded and looks almost the same as the concrete that it's on. Right? And the sun's coming straight at it, so it's hard to then do image manipulation, because anything that you do is going to affect the whole image. All of it's going to get brighter, all of it's going to get darker. So how do you tease out where that line marker actually is? So these are examples of current people's user stories, as we'll talk about going forward. And you can imagine there's whole teams there, and multidisciplinary teams, engineers, mechanical engineers. They probably got someone that is out of physics and knows a lot about light. And how it refracts, and how it can be processed, maybe computer graphics expertise, and then straight up software devs that need to, once we know how to solve this problem, have to put it into production and make it all go. So as software engineers coming out of this, we have to be ready to tackle extremely complex problems. And this is a case where a company really wants to be able to use this as a feature to sell their cars down the line. So we can't just put this off and say, well, it doesn't happen very often, we won't handle it. Can't do that. You've got to handle it. So someone's got to be working on this and teasing it out. And of course he says, almost ready to release. So, saying this is the final thing we need to solve, but it sounds like if he, as a CEO, if he's going to go public and say we're almost ready to release this, it means they probably do have a handle on this. They're just trying to get it through the last little bits of quality assurance and testing. But this is high risk testing, so this is critical, what we call safety critical contexts, where if it fails, people could die. And so you have to do all your due diligence and make sure you're really confident that the software will work in most cases in these things. And we'll talk more about software testing as we go along, because it is impossible to get to the situation, the state where you can say, yes, we know our software works in all cases. Right? That's just impossible to do. So then you have to you have to then decide, how much of this are we going to do? How many cases are we going to cover? What's good enough? What's legally good enough, right? So if we do all of this stuff and someone uses our software and still dies, how legally liable are we going to be? What defense can we mount? Can we show due diligence? What is due diligence? All that kind of stuff becomes very incredibly murky. And so this should be enough to make you want to scuttle back to your programming class and just, I'm just going to be a programmer. I don't want to learn about software engineering. I don't want to deal with all this. But that's the unfortunate reality, is that all our skills that we learn in programming classes, as we move into the engineering role, we can't abstract the world away. The world impinges on various ways. Not all of them are technical. And as people that are very excited about the technology, we have to understand that we also have to understand the sociology, the regulations, all those sorts of things, or at least be on teams where there are people who understand those things and can help us navigate them. All right, so the goals, as I mentioned, is to present a fundamental introduction to software engineering. I'm going to present a brief history of the field, along with some foundational theory behind software engineering. We'll survey lots of software engineering concepts, terminology, and techniques. And then we're going to take an in-depth look at two important software engineering concepts. One of those is software development life cycles, and in particular, this whole notion, relatively recent notion of things called agile methods, and how those integrate with our understanding of traditional software development methods, and what are some of the good practices. Are they universally good, or if they're not universally good, how can we integrate them into more standard or more traditional life cycles? So we'll be looking at that. We're also going to look at designing and implementing concurrent software systems. And if I can get my act together, I'm going to change that this semester to also be concurrent, distributed software systems. Now we have whole classes related to distributed systems, and I'm not attempting in any way, shape, or form to replace that class at all. But increasingly, as software engineers, we have to work in distributed settings. So we'll have to be dealing with data sets, for instance, that can't be stored on a single machine. And so as soon as you can't put your entire data set on a single machine, you have to adopt a data store that can be distributed across multiple machines. And as soon as you go to the distributed notion, all sorts of things come out to bite and make the software engineering of those systems ever more complex and ever more difficult. So what I do in this case is that, we talk a little bit about threads, and we talk a little bit about parallelization, and what's the difference between parallelization and concurrency. But in this class, what we're going to be looking at is what are the best design practices. Why do we want concurrency? How would we design our systems for concurrency? Once that is, how do we protect ourselves against all the problems that pop up when we've got concurrency or distribution. So we'll be very much looking at it from a software engineering perspective. And then you can still go to those other classes and learn all about it from a distributed systems perspective. They got a different whole layer of abstraction that I'm going to put on top of their field, which we won't discuss. But if you step into that class, you'll peel back and go into that and see all the murky details in that class. And then, with your help, and I'll talk a little bit about this in a few slides, my goal is to explore a wide range of software engineering techniques and tools, software frameworks, and more via one of the kind of long-standing projects in this class for you. And there'll be an opportunity for you yourself to learn at least five new frameworks or tools or techniques or methods. You get to pick and go in depth on them. And then across the whole class, if we take all these people that we can see here in this room and multiply by 5, that's a pretty big number of things that we can explore together as a class. So a little bit more detail on that in just a minute. Now, who am I? I'm an associate professor here at CU. I've been around now. I've been here for 17 years, so this is the start of my 18th year. It's my start of my 35th semester here. I got my PhD at UC Irvine, where I was working with a software engineering research group there. And we were looking at the time, software architecture and user interface development systems. Also, a little bit of event-based messaging work went on at UC Irvine at my time. And my specific focus was on hypermedia and how to use it in software engineering. So this is my 9th time teaching this class. Every time that I teach it, I try to reboot it just a little bit so that we're looking, the technologies I discuss, try to keep pace with maybe what was current last year or sometimes current this year. Everything changes. One of my favorite web cartoons is one of a JavaScript development shop, and the developers are sitting throughout the room, and someone says, someone just posted something slightly different on how to do JavaScript web development, so we have to reboot our entire tool chain. And they slap up a 0 on top of time since last reboot of JavaScript tool chain on the wall. So things go very fast. My own research interests are in kind of software engineering related topics and in the design of web systems, web-based systems, along with software architecture of very large systems. And I work on a project here called Project Epic, which looks at how people use social media during times of disaster or crisis. And so we have people who are on the human-centered computing side of things, and they study the behaviors. What do people share? How do they share it? What do they say? How is it similar across events? All that kind of stuff. And what I do is collect all the data. So my team is in charge of taking millions and millions of tweets that come across the streaming API and storing them in a way that we never lose them. They're replicated. If one machine goes down, we don't lose the tweets. And we can handle surges. So normally we get about 2 tweets a second, but on a very big event, such as the Nepal earthquake or the Japan earthquake a few years ago, they can spike up to 100 tweets per second. And that's, that's a 2 orders of magnitude there, and you have to be ready for those types of things. So that's kind of what my research group does on that. And then when I'm not being a professor, all the rest of my time goes to the 3 kids pictured on the right. So they keep me very busy as well. So office hours, shoot. I imagine that does not say Fridays 2 p.m. to 3 p.m. there. I meant to say to be announced. I still haven't quite decided what to do. That's a carryover from last year. Where the office hours will be, though, is in DLC 170, which is over in the Discovery Learning Center, and it's going to be in this big red rectangle there, which is on the 2nd floor of that building, which is somewhat confusing. The first floor that you come into, as we Americans say, the first floor in there is actually the basement level. You go up 1 to be at the first floor. So I will, in general, I'll say, please send me an email to let me know that you plan to stop on by. And by Thursday, I'll have the actual time. So sorry, just ignore that for right now. All right, so there is a class website, which is up and has the slides for this lecture already. And so you can go to my webpage, which is www.ucscolorado.edu/Kenna. And then, actually, if you just go to ~Kenna, right up on the top nav bar, there's a link that will take you straight to this one. But I always have classes, the class number, and then the semester number to distinguish them. And I would like you to check the website every day. I really am serious about that. So if there's a homework assignment out there and I get 6 or 7 questions that are all the same on the particular homework assignment, I will most likely post my answer to that question on the What's New page of the website. And then if I remember, I might also push it out on the mailing list, but I do more work on the What's New page. So even though you might get bored and not do it every day, just try to get it into your cycle of swinging by and checking that What's New page for any announcements. There is an RSS feed. I realize RSS has kind of had its peak and is now fading. Not as many people use it now, but there is an RSS feed on that page, and if you have something like Feedly or NetNewsWire or some of those it used to be I could just point people to Google Reader and everyone could find a cross-platform tool, but they shut Google Reader down. But those things will allow you to subscribe to the feed, and then you automatically get updates as I post them. But the website is where I'll be posting the class schedule, the homework assignments, announcements, etc. And that is my primary means of distribution to you. Now, I also have, if you go to MyCU Info and then click on Desire to Learn, and you see the 5828 website for this class. Sometimes I will use that website sometimes to hand you things. So if I've got like a file I want you to read, like I do today, this week, that's there on that website. That makes it so it's not publicly available, but a place you have to log into to get it. And I'll be using D2L as one of the ways that you'll be submitting homeworks to me. So there'll be 2 ways of doing that. One is through D2L. The other will be through GitHub, and I'll make it clear which one you should be using. Okay, the textbooks this semester are going to be These two, they're both from Pragmatic Programmer, and you can get just PDF-only versions. That's what I actually have. I don't have the hard copies for either of them. But they're available at pragprog.com. And the first one is called The Nature of Software Development by Ron Jeffries, and the other one is the 7 concurrency models in 7 weeks. And so these two roughly correspond to those special focus topics on agile life cycles and on design of concurrent software systems. The 7 concurrency models in 7 weeks is one which we'll use to expose ourselves to other ways of designing concurrency in software systems, other than, the traditional way is to say thread T equals new thread, and then start, right? And then my run routine will be called, and then I'll do everything in my run routine. The current best practice is you should never have new thread ever anywhere in your code. And so through this book, we'll look at ways in which you can actually achieve that, to just get away from threads completely. They'll still be there, but again, we put a layer of abstraction on top of them. We no longer have to worry about getting those things started, and instead we work at a higher level abstraction, makes less errors, and higher, clearer expressions of the problems. And then The Nature of Software Development, Ron Jeffries is a name that has been around in the Agile world and also the object-oriented design world for many, many years. He advocates simplicity always, and so what I love that about his philosophies. He's also a pragmatist, so it's not like he's saying it's Agile only or waterfall only or anything like that, but he tries to convey a sense of what should we value in any situation I find myself in, and how can I use that? How can I use those values to drive any context that I'm in towards something that will allow me to be the best software engineer that I can be? So I like this book in terms of the overall philosophy, but of course it's not going to be a complete introduction to Agile life cycles. So I will be supplementing material that I've created in previous versions of this class and from other textbooks and other books that I've used throughout the years. So in fact, actually, here, every year when I have to figure out what's my textbook going to be, I just kind of pick 2 that are useful. But in actuality, on the Agile software lifecycle side, I've got about 10, 12 that I draw material from. But I think if I were to list all 12 here, I don't think you'd be very happy with me. So instead, I'll be pointing to these books. I'll say, okay, so today I'm pulling material from this book. It's a great book, but it's not required. If you're interested, you can obviously go get it, but I'll just pull in what I want from those other sources. All right, so the 3 main topics. The first one is the introduction to software engineering. I just want you, when you leave the software engineering class, that you know what requirements are, design, testing, maintenance, what the waterfall model is, what a prototype-based life cycle is, what's an agile cycle, or what's the agile philosophy, and then there's various agile life cycles, Kanban, there's, I don't know if I'm pronouncing that correctly, Lean, there's Scrum, there's Extreme Programming. All of those are life cycles that try to follow the Agile philosophy, so we'll be talking about those. And then, as I mentioned, we'll be talking about this design and implementation of concurrent systems. Something I didn't mention previously, what drives the need to understand how to work in concurrent and distributed systems is that the days of waiting for faster hardware is pretty much over. Right? So I lived at a great time in my own student career for the wonders and wonders of the computer hardware world, where every 18 months, things got twice faster, easily. And the memory size doubled every 18 months, and the amount of disk space doubled every 18 months. And so we used to say things like, well, if your system's not performing well, just wait 18 months. It'll be running on new hardware that's twice as fast. Problem solved, right? Unfortunately, that was a logarithmic curve, and we were on this portion of the logarithmic curve. At least that's where I was, where it was going up very, very quickly. And now, as logarithmic curves do, they tend to level out. Right? And so now we are on the level out phase, where if you actually go take a look at the chip speeds you can buy today and go back 3 or 4 years, they're not all that different. It hasn't gotten that much faster. What has gotten different is how many cores are on those machines. right? So things, they like to say it hasn't gotten faster, it's gotten wider. And what we mean is that the multiple cores on the chip can do more things at once than we used to be able to do. And by doing more things at once across, even on one machine, you can get more work done. But now if you have multiple machines all working together, each of them able to do more things at once, you can suddenly get extreme speed-ups in what you're able to do, but you have to design for it, because no longer is it a single-threaded world. Right? Now you've got distribution, coordination, and concurrency or parallelism coming in. So that's the reason why I view it as a software engineering topic. We, as software engineers, can no longer afford, it used to be that, parallelism in programming languages was a niche topic. If you were in programming languages and wanted to get your PhD in compilers or something like that, you would know about parallelism. Or if you were on the system side and you were doing chip design or operating system design, you had to know about parallelism. But software engineers, we could go to work and not know a thing about it and produce great software that everyone loved. No more. Now, if we want to see great performance gains, we have to be designing for what our machines now provide. All right, and then as a class, we're going to be exploring lots of software engineering techniques, which I'll discuss in just a second. So this is my current plan for how I'll be evaluating the course. There's going to be a 5% class participation and attendance portion, and that one of my goals will be to learn people's names, and from that to get a sense for, oh yeah, this person's always here, or that person's not there. So I won't be taking official attendance at the beginning of each morning, but I will, or each class session, but over time I'll get a feel, and then, and then there'll be lots of opportunities for you to participate in ways that leave records, so I can at the end of the semester say, oh yeah, here's where they participated, here's where they invested their time. We'll also have occasional quizzes. Now last year I was able to get 3 quizzes created and deployed, so there's definitely going to be 3 quizzes. The fact that they've been created now gives me extra time to create some more quizzes, so I might actually have a few more this semester. Homeworks is going to be a thing where I'll be sending out, I'm going to try to do it maybe once every 2 weeks is the current plan, and they will always kind of try to reference back into the lectures and have you apply the topics or answer questions about the topics so that you're forcing yourself to say, oh, Ken talked about agile life cycles, so I can't write any code for that, but here are the basics. What are some of the principles? What are some of the values? To be able to write those out in an intelligent way. The midterm will be in week 8, and will be on whatever we cover by the time we get to week 8. And then the presentations is the new thing this year, in which I'm going to be having you creating presentations on software engineering frameworks, technologies, programming languages, etc. Throughout the semester. And the presentations will be submitted on GitHub. Quizzes will be taken on D2L, and homeworks will be submitted via D2L. So that's kind of the basic overview of the grading. So the midterm is going to be, it's a done deal. I always have my midterm on Tuesday of week 8. So this semester, that is October 13th. Also, I advise if you don't currently think about semesters being week-based, like you should be able to say, if I were to just come up to you randomly in the hallway and say, what week is it? You should be able to say, week 7. Like, right away. No, this is week 1. We've got 15 weeks in the semester. We ignore the fall break week and don't include that in our numbering. But you should know where that week is. So if we're in week 6, you know 2 weeks from now, Professor Anderson's holding his midterm. He always holds it in week 8. Right? So get that in. I just put it in my calendar every Sunday, week 1, week 2, week 3, week 4, just so it's there. Now, if you are, I don't have anyone that's attending remotely, but I do have about 6 or 7 students that are in the Be Bolder Anywhere section. So for those of you watching this lecture later, you're going to have to work with Be Bolder Anywhere to set up a test proctor. That can be someone at your work. That can be the people that work at Be Bolder Anywhere. It can be a librarian. There's all sorts of options. Work with them to get yourself a test proctor, and then that week of week 8 to week 9, you'll have a 1 week to schedule with the proctor and take your midterm. All right. So presentations. This is an evolving idea. It's a brand new idea. It's one that I haven't done before, so bear with me. This is my current way of thinking about it, and it could very well change as we go across the semester. I'll be open to feedback from you as to how it's working, and we will try to make it work, come to something that we mutually like as we go through the semester. So what I want you to do is to have a chance of really deep diving into other topics that I won't have a chance or a time in lecture to cover. The benefit to you is that if there was something that you've been hearing about but you've never had a chance to explore, you can now use my class as an excuse to go explore it and have an opportunity to report back to your peers about what you learned. And the idea is to look at things like software engineering methodologies, so testing methodologies. There are things out there called regression testing, black box testing, white box testing. What are these things? And maybe you should go in and learn a little bit more about it and write up a presentation on it. There's some whiz-bang new programming language out there that's supposed to make distribution easy. Well, let's go take a look and write an example that shows how it makes it possible to, instantiate 5 or 6 processes across 6 machines and have them all talk together with very little effort. If there is such language out there, we'd like to learn about it. So go and pick that as your topic and write about it. So what I'm going to do is on Thursday, I'm going to do this for a technology that I've picked, and I will show you what I'm kind of looking for. So I'll have on GitHub a repo of code that will demonstrate certain aspects about it. In the repo, there'll also be README files and other kind of markdown files that explain things that I've learned about doing it. And then, as I'll show, there's a way for GitHub to host a website for any repo. So once you've got a repo up onto GitHub, it's the work of like 4 or 5 minutes, and you could also have a website that's available on that same repo. And on Thursday, I'll step through the whole process of creating it, and so you get a good handle for it. And so then you could decide, if this is a text-based description of what I've learned primarily, there's not much code available, then what I'm going to do is create a website and have the website be my presentation of the material. It will be linked. You can go and see various things that I've learned. If it's a programming language and I'm going to show a few examples, then your code sits in the repo side and your presentation sits in the website side. And you can do this all for free on GitHub. I'll step you through it. And so the idea is you'll have 5 of these presentations to make throughout the semester, and they'll be due once every 3 weeks. And then once we've gotten through our first iteration, where all of you produce 1 presentation 3 weeks from now, one of the things that will come online is that I'll ask you to go look at other repos produced by your peers and give you some number to go look at and review. And if you see something that's weird and you want them to address it or to answer it, you can create an issue. If you looked at their code and thought that maybe it wasn't quite right, or maybe it could be improved, or here's another example, you can create a pull request, which they can then review and incorporate into their presentation. And the reason why I'm doing all this is that these are things that are very useful skills as software engineers to have. Out in the open source community, this is the coin of the realm, the ability to work on projects, submit issues that, you're identifying an issue, but you should phrase it in a way that's not pissing off the owner of the repo, otherwise they won't respond to your issue. If you're going to be, really super helpful, you're going to do a pull request, and then your pull request is going to have to honor the code conventions that they have and their approach. You can't say, oh, here's my pull request. It replaces every piece of code that you wrote, and here's my code in exchange, right? That will never fly out in the open source world. So it'll have you think about, oh, well, how should I communicate this change request to my peer? With the goal of, if they accept the pull request, your change gets into something that is, that they worked on, care about, created. So there's an ulterior motive in terms of getting you very comfortable in interacting and working with GitHub in this way. All right, so a couple of honor code things. You're allowed to work together in teams of up to 2 people on the homework and the presentations. But while the quizzes, of course, and the midterm are individual work. If you want to have more people on your team, let me know and I'll consider it. But I will have higher expectations the larger your team gets. And so if I get a repo from a four-person team and it looks like one person spent 10 minutes on it, that won't be good. But if a 4-person team comes in and just knocks my socks off with videos and what have you, then that'll be great as well. So the student honor code will then apply, of course, to the quizzes and the midterm, and that's usually pretty easy to do. Just take the quiz by yourself. Don't ask someone who's taken the quiz what their questions are, and we'll be good. Otherwise, the homeworks and presentations, I encourage collaboration. I like to see it. Yes?
Does that mean if you work in teams, only one person will be submitting, or does each person actually submit?
Yes, so that's a great question. Whenever there's a team, I just want one submission. Otherwise, even with the best of intentions, I'll see 2 or 3 submissions come in from everyone on the same team, and for whatever reason, someone posted an old version, and then I'm looking at 3 different versions of the homework. So yes, it'll be just one submission per team. And then you'll just send me an email to say who submitted. Yes?
So is there no final for this class?
There's no final for this class. Yes. So it'll just be these presentations currently. There will be homeworks, so the homeworks will be something that'll be going in parallel with the presentations.
Okay, and we're not going to be doing presentations during like finals week or anything?
No. Yeah. Yes?
In previous years, you also had a final project?
Yes.
That?
So I probably won't do that. I'm going to see how much work these presentations actually are. Because they are going to be encouraging examples, right? And so you'll be doing programming to demonstrate what you're learning.
One more question.
Yes?
About the methodologies and things that we will be researching, is it more focused toward what is being used in industry now, or what is being used, or can we approach it from like what is being used for like teaching younger generations for the next?
Yeah. If it's got something that's got a software engineering slant to it, you just send it to me, and I'll most likely give it a thumbs up. And it's even fine for historical techniques. We used to do this, but we don't do it now. Here's what I learned about why they thought it was good. Here's why it failed. Those would be good as well. The key thing that we'll have to watch out for, of course, on describing methodologies is that you'll be obviously referencing other things that you've gone out to go read, books or blog posts or other sorts of material. You have to be very careful when presenting this material that it's your own words, and that you don't, I shouldn't be able to select the text on your page, paste it into Google, and be taken to the page where the text came from, right? So we're going to have to watch out for that, but that's why I have multiple of these across the semester. The first one is going to be a chance for us to establish norms, what's expected, what's kind of too little work, what was too much work, what's just right, and what are good practices for citation, to present things, that kind of thing. So our first go around in 3 weeks' time will be a chance for us to experiment. What do we want? What do we don't want? What's good practice? What's bad practice? And I'll be making this more explicit as we go along, and I hope to give you a good example to mimic when I present it on Thursday. Okay. Last thing is for the homework assignments. Which is all this, and the presentations, you can submit them up to 1 week late. If the repo comes online after the deadline, or the assignment is submitted after the deadline, then you just get a 15% penalty applied blanket. So that'll, of course, take you down into the B range, and then you don't want to do any more mistakes after that so that you don't go down into the C or D range. Just try to get them on time. It would be good in this class to not let things fall behind, because then you've got to be doing the current assignment plus trying to get the old one submitted. And I try to, as I did like today, I try to get my lectures out early. I try to get my homeworks up early. You'll have plenty of warning about when things are due ahead of time. So one thing, of course, that's very hard to work around is the midterm. And even through the 8 times I've taught this class previously, it's not quite one student per instance, but it's maybe one student every other instance who forgets that the midterm was on on the Tuesday of week 8, doesn't show up to that class, shows up on Thursday, and I say, okay, well, midterms aren't finished grading yet. I'll get, and they'll be like, what, the midterm was on Tuesday? So don't forget about that. If you know you can't be here on October 13th for whatever reason, it's best to get in touch with me before the midterm. Then I'm happy to work with you. If it's after the midterm, I'm not so happy to work with you. I'm not as flexible. All right. So last boring thing, and then we'll get into some content. Syllabus statements. The university asks me to present various policies at the start of every semester. This includes things like disability accommodations, religious observances, classroom behavior, discrimination and harassment, the honor code, etc. So I have that up on the website at this link. And I'll be posting a What's New item that also points you to it. Take a look at those things. In almost all cases, the policy to know about is if you're asking for an accommodation, especially for either a disability or because of a religious conflict, it's always best to get a hold of me early. And then I'm happy to accommodate. We'll work around whatever needs to be done. Just don't come to me after the fact. It's so much harder to respond in that case. Okay. All right, last thing as a kind of bookkeeping thing is programming languages. So if you take a look at that book, The 7 Concurrencies Framework, you'll probably see a lot of programming languages that you maybe have only heard of or have never heard of, like the Elixir is a pretty obscure language, Clojure. But I'll be presenting code examples throughout the semester that come from all sorts of different programming languages. So Java, Objective-C, Clojure, Elixir, C, Ruby, Python, possibly more. The point here is to say that as a software engineer, you have to use the right tool for the job. And it could be that you love a particular language and you only ever program in it, and then you get into a professional context and they're like, yeah, the legacy system is in language X, and it's not your favorite language. You can't say, oh, well, I'm going to rewrite that whole system in my favorite language. Won't be possible. You'll have to learn how to pick up and move to that other language and work in it. So the goal here is to say that, be open. Start, if you haven't already achieved this skill, and it's a critical skill to have, be open to being able to read other languages, in programming languages. There's a ton of concepts that are the same across almost all languages. It makes it possible to adapt your understanding from one language to the other. But be prepared to be agile in understanding code and learning code, picking up new code. Now, when I get to those chapters in the book that depend on Clojure or depend on Elixir, I always start the lecture with an intro into the language to say, here's what this means, here's what this syntax means, that kind of thing. So I'll bootstrap you, but there'll still be, for you to really grok it and be able to answer a question on the homework or the midterm, because last year I had questions that touched on the Clojure material on the midterm, and either that page was either completely filled out and they got everything right, or it was blank. It was like, oh, this person never learned Clojure. They were just kind of watching me talk about it, but not really learning enough to be able to answer the questions about it. So, but in general, I'm agnostic on programming languages. So I'm not going to say in your own presentations that you turn in with code that the code has to be in some language. That language should be, if you're talking about, say, for instance, Solr, which is a search engine, and you want to show examples on how to program and use Solr, then and why it's useful to software engineers, then Solr comes with a huge number of language bindings. Pick your favorite and use that language binding. I'm not gonna worry about that. On the other hand, if you're like, ooh, Elixir's this bright, shiny new language, I'm gonna show how to use Elixir, you're not going to be using some other language. You'll be using Elixir in that case. So, but otherwise, I don't typically will require it. Unless, so for instance, I have one homework assignment that has a Java program which doesn't work. It's not correctly designed for multiple threads, and bad things happen when you run it. And in that particular assignment, you'll have to use Java. Right? So there will be a couple of times where that'll happen. All right. So what I want to do now is, for everyone that's got a laptop, or people sitting next to people who have laptops, I'd like to just get a sense for what people currently know about software engineering, and we still got plenty of time to do this. So the URL is right there. It is bit.ly, so http://bit.ly/ and then it's 1NQ, both capital, then C lowercase, Q uppercase, and then LQ. And what I'd like you to do is go to that page and use the magic of Google Docs to, I'm personally not connected to the internet yet, but use the magic of Google Docs to just start filling in things that you know about software engineering currently. And we'll spend maybe, I don't know, 5 to 10 minutes on that. All right, I need to be over here.
What was the link?
I got the same thing.
1N.
All right.
Oh, I missed the end.
So this link should have been anyone, if you're using your colorado.edu Gmail account, anyone from CU Boulder should be able to have access to the document. Are people getting permission denied
Yeah, I can.
messages?
It's an
It's an I, not an L.
Oh, it's an I, not an L. Okay. So where's that one? Oh, at the very end? Yeah, yeah. So capital Q, then L, and then lowercase q. At the end there. Anyone still need the link? Okay.
EQ, IQ. Yeah.
Are we all editing this at the same time? Which one is a capital I? This one?
And then, yeah, you'll start to see people filling things in, and I encourage you to just find a section you know something about and add a response.
Which one? 大写的哈。
Big N.
Start reading something and just jump.
Okay.
And if you don't have a device, then you can always scooch over, introduce yourself to someone who does.
Dude,
Are we good on the URL? Okay.
Methodology.
you're typing.
You got it?
All right. Somewhere here's Zoom. There it is. Let's zoom in here.
Good Lord.
Good.
You need to use the fan.
It's just a typing free-for-all.
Right. One. Q, I,
You need
capital.
to use this one.
Okay. Other term.
Write out. I can only use Chris's.
This is my first time ever having, massive denial of service attack on Google Docs. So it's interesting to see how it works.
Signed in to Chris right now.
different kind of key.
Different.
To add on all the questions.
Yeah,
Add answers.
So for those of you who don't have a device, here are the things that I'm sort of asking. What's your definition of software engineering? What software life cycles do you know about? What stages in a software development life cycle do you know? When you think of tools that you use when performing software engineering, what do you think of? And when you think of methods that you use when performing software engineering, what do you think of? So basically a definition, life cycles, stages of the life cycles, tools, and techniques. And just kind of, I'm interested in knowing what you already know.
Everyone's answer.
I think they just need to completely different.
Yeah, just watch. I think you can go back.
Implementation test, I think it's a tool. When do you think of methods? What do you think of
Yeah.
what do you think of? Excellent.
Not that much there.
Yeah, I don't know a lot either. I don't know if I can answer you.
I'm just caught up reading other people's stuff right now.
That's good too.
Yeah, reference system, man.
Is not sure a valid answer?
Yeah,
All right.
Bad concurrent system.
that's something you think of. That'd be great.
I'm not surely agree.
And so this is not a situation where you need to go to Wikipedia and look at things for software engineering and then put it in. I'm just interested in what you know as a kind of default starting state.
Yeah, I get that.
And I'm pleased to see what I'm seeing already, which is good. This is great. We'll go for 2 more minutes just because there's more things I have to cover before we end. So just 2 more minutes, just put a few more things in.
Yes.
I can't remember any of those.
Or like it's like this is a different question. Bugzilla था? Oh हाँ Bugzilla होता है.
All right, one more minute.
Requirement analysis. Review code inspection.
Okay, great. Thank you very much. So let's just review and see what were some of the entries that were put in. This is great. So under the definition of software engineering, we got software is a set of instructions that does some operations. Engineering is the application of creating something that helps people. That's nice. Software engineering is the application of conceptualization, design, building, test, and maintaining a set of instructions, a program. The process of developing and maintaining software during its life cycle. Developing software projects over an extended life cycle. Scalable software architecture, just being able to anticipate a market for your software, the scale of that market accordingly, so bringing in some market concerns, which is good. Software engineering is to make what we thought come true by using programming tools. Exactly. This hits on a very key point. Software engineering really is a creative discipline. You can, there's actually a person that I'm going to have you read today and tomorrow before Thursday's lecture is Fred Brooks. And he talks about in some of his essays just the sheer joy of creation that we get when we produce software systems. Oh no, someone's selecting all, I'm going to delete it, don't. So I would look at the history. I think there's history. We would find you. No, just kidding. All right. What else do we have here? Software engineering is the process of conceiving, the process of using code to create programs to accomplish tasks. Now that's pretty interesting. I like that one. It kind of edges into some of the stuff you see in software or sci-fi books. Some of my favorite sci-fi books are where there are characters who are programmers. So programmers who are, in the year, several centuries in the future. And science fiction authors thinking, like, what would programming be like 300 years from now? And oftentimes they have a human who's the designer, and then they've got AI routines that kick in to do the actual coding and building and exploring alternatives. It's always fun to kind of think about that. So here you have this kind of a hint of that. We use code that then creates programs. So you have some code you're writing, which then helps you create programs. And you're doing that because then it helps you accomplish tasks. Software engineering is the process of conceiving, analyzing, implementing a software program using a specific set of software tools and techniques targeted at a particular system or set of systems. That's very nice. Okay, some software life cycles. Prototype-based development, design, build, test, maintain. That's kind of saying a life cycle name from the steps that we follow. Agile, Scrum, Agile and Waterfall. Incremental development, Waterfall and Agile. Kanban or Kanban, I don't know how to pronounce that thing. Iterative, Agile, Waterfall, test-driven development. What are some of the stages of software development? So feasibility, that's great to see. A lot of people forget about that one. So should we build this at all? Is it even feasible? Maybe it's technically feasible, but is it politically feasible? Maybe not. Is it financially feasible? Maybe not. So feasibility, development, verification, validation, maintenance, commercialization, requirements analysis, design analysis, security. That's a great one to see. Testing, because most people glom security on at the end. It's too late. Quality assurance, resource gathering, refactoring, design, development. Yeah, so all these are in some way or either related to or are a kind of a stage that you'd see in software development lifecycle. All right, and here's some of the tools when performing software engineering. So people thought of Eclipse, Selenium, Bugzilla, Waffle.io, Amazon services like EC2, things like GitHub and Subversion, Agile tools like what Rally Software here in Boulder produces, Vagrant, Ansible, Valgrind, GDB, Trello, Source Control, so someone, more source control systems here, Perforce and ClearCase and so this is interesting. Use cases, high-level designs, algorithms, test cases, debugging tools, frameworks. So yeah, some of these could be methodologies, but yeah, they're also tools at a certain abstract level. IDEs, and then here's a great one I like to see, whiteboards, Perfect. Debugging software. That's a very useful tool. Dolphin. And what I love about this, what I love about being in software engineering, being a software developer, is that I don't know everything that's listed. There's always a chance to learn something new as a developer. Now, you always have to triage, is it worth my time to learn this something new? But there's just a ton of ways to do to all do the same thing, and there are new things to check out. I think I've seen Selenium before, but I have no idea what that is. So what is Selenium?
It's a web-based, it's for testing web pages.
Okay, so it's a testing framework. Cool. All right. So, and when you think of methods for software engineering, what do you think of? So here we have object-oriented programming, test-driven design, behavior-driven design. Scalability, that's a characteristic, right? We want our systems to be scalable. Prototyping as a method. So we don't know what we're going to build, so let's build something quick and easy, and then let's see what they think. Not sure. That's a good one. That's why you're taking this class. Incremental development, the spiral development, that's pretty cool. That's an obscure academic reference there. Throwaway prototyping, which is great. Design patterns, yep. Singletons, which is an example of a design pattern. Machine learning, and I'm starting to see more machine learning work creep into software engineering research. Threads and continuous integration, extreme programming. Great. So this is good. So what that tells me is that you have all in some way encountered stuff that's related to software engineering. And what I'm going to try to do is knit things together. How do we categorize these things? What is this versus that? If we talk about this as being a method, what does that mean as opposed to it being a tool? And how do those interact? So methods typically have sets of tools. Phases will have tools that we'll use during those phases. Or we might use one tool across all the phases, but it's present in each one, and how does it play a role? We'll try to look at a lot of those issues. One thing that didn't pop up anywhere is estimating, which is something that we have to do every day as a software engineer. Someone says, when's it going to be done? When's it going to be done? We're working on this thing right now, this feature. When's it done? I don't know. Right? How do we go from, I don't know, to, oh, it'll be done in 3 days. We think it'll be done in 3 weeks. Right? How do we make those estimates? Now, this is where that issue alone of estimation is the Achilles heel so far of software engineering when we look at other engineering disciplines. Because if you look at mechanical engineering, they build a bridge. They say, okay, so what's the average wind speed in this area where the bridge is going to be? Yep, okay, it's that. How long is the bridge going to be? Okay, good. And what do we know about the foundation, the bedrock that we're going to be building with? Tell me about that. Oh, there's clay, but the bedrock's 2 miles down, or whatever that is. Then they go, okay, here's our catalog of bridges. Thump, thump. There's the wind speed. There's the foundation. Here's the length. Here's your bridge, right? And they've gotten to the point in mechanical engineering where they can do that pretty much almost like I just showed you. And then you can say, yep, that's the bridge we need. Let's order it. And then a couple weeks later, helicopters, here comes your bridge. Right now, so now why? And they can say, yeah, it'll cost you X amount, and it'll take us 3 months to produce it and then get it installed. So why is it that mechanical engineering can do that? Whereas if you come to a team of software engineers and say, hey, we'd like a web app that does X, Y, and Z, we can't say, oh, that'll be done in X, Y. It'll be done in X months. So what would be an intuition? Why is mechanical engineering able to do that and we're not?
I think
the consumer requirements keep changing dynamically.
Okay, that's a good one. Yep. Alex?
It's a different problem you're solving every time.
Different problem you're solving, so the problem shifts, and that's kind of what you were saying with the requirements, yep?
They've been around for years and been doing mechanical engineering for centuries.
Centuries. They're centuries ahead of us, right? How many things can you say where that's true? But yeah, humans have been building things for 5,000 years, maybe longer. That's a lot of expertise to know you don't build an arch this way, it falls over, right?
I think one of the biggest differences is that for mechanical engineering, to get them a new bridge, you still have to build the bridge. Software, if somebody wants an exact solution that's already been come up, and just copy it. Then it takes like a half of a second.
That's true. There are certain situations, certain domains where we have well-known solutions, and if the old solution A can be adapted to new problem B, like that, it's just a small variation, well then, yeah, then that could happen very quickly. Yeah, that's true. Our materials are copied very quickly. That's a fundamental difference there, exactly. Okay, so this is great. Now what I'll be doing is hopefully enabling you to categorize these things and to understand where each of them fits into a software development process, and hopefully open your perspective up to the fact that I need to be willing to tackle and learn new things all the time. And for me, that's what keeps me going. Every time I reboot my system, or my class, it's because I'm about to learn something new as well. And that just gets very exciting, at least for me. All right, so here's a couple of definitions that I've used over the years. So one way to break down software engineering is to look at the two terms in particular. So software is computer programs and their related artifacts. So the key part there of that is the and their related artifacts, because we all are familiar with programs and taking source code and compiling them to binaries and launching them. But then there could be requirements documents, design documents, test cases, UI guidelines, usability tests. All of those things we like to think of as the software, not just the bits, but everything in context that was used to develop those bits. And then engineering is the application of scientific principles in the context of practical constraints. Right? So this notion of practical is a key notion. So I like to ask people, what's the difference between chemistry, which is performed on the other side of campus, over on the arts and sciences buildings, and chemical engineering, which used to be performed in this building and is now on East Campus in the new biotech building. So what's the difference between chemistry and chemical engineering? Why do we need two disciplines?
Well, chemist is nothing like a chemical engineer. Chemical engineers may have nothing ever to do with chemistry at all.
Oh, that's interesting. So chemical engineers have nothing to do with chemistry?
I'm a chemist.
Oh, you're a chemist, okay. Oh, interesting. So there's never a time where a chemical engineer will take a result from chemistry, though.
They will take a result, but they don't actually do the implementation of designing the actual chemical.
Yeah, or the chemical or the techniques, right? So the way and you can test me on this is my first time I have a chemist in the room. The way I explain this is that a chemist might be looking at a particular research goal, which says, how can I make a reaction possible? And in the research setting, it might be just enough to say the reaction is feasible, right? Or we have to bring this in and this in and this in, and the reaction occurs. And beforehand, we didn't know how to make that particular reaction, that particular effect occur. Now, if it turns out to be something that would be really useful to society at large, the chemical engineers have to come in and say, how do we scale this up? How do we make this work in a practical way? How do we make it cost effective? Right? The chemistry will stop with the science behind it, but then there's still the notion of deploying the knowledge that has been gained. So how does this sound?
It's somewhat, somewhat, yeah.
At a high enough level, I would say.
High enough level, yeah.
Yeah, okay. So, my example I like to use is consider taking salt water and converting it to fresh water. You might have all sorts of interesting techniques that you can do at the small scale to say, oh yeah, that's drinkable once it's done. But a chemical engineer will have to say, how do we make this possible for a region to take all the salt water from the ocean and convert it to fresh water without waiting for the natural process to occur?
I would basically say a chemist doesn't worry about reproducibility as much, but a chemical engineer is very much about reproducibility.
Okay, great. Yeah, so if they can make it happen once, it's good, but a chemical engineer's got to make it happen all the time. Yeah, exactly. And that's true of more engineering disciplines in general. And so same thing here with software engineering and computer science, right? So there is a difference between computer science and software engineering. And then when you talk about computer science, you can say, oh, well, there's algorithms, there's distributed systems, there's networking, there's all these kind of, there's proof techniques, right, for understanding whether a program has a particular property or not. Those things are all part of the broader topic of computer science. And software engineers have to look at those techniques. You have to understand your algorithms. You have to understand your data structures. You have to understand distributed systems, all those kind of things, and weave them together to produce some sort of practical, in some cases reproducible result, so that day by day, your day after day, your software system is running and producing and doing its functionality that it was designed to do. So we need to make sure that we are able to scale things up, make them reproducible, make them reliable, whereas the data structures person might just say, here's one way that we could create a data structure that minimizes the number of disk reads we'll need on a database that's distributed across 10,000 nodes. So they might come up with that data structure, and then it's up to us to say, well, how do we make sure that data structure doesn't consume so much memory that it causes our system to crash? A software engineer might do that work, whereas a data structure person might just say, okay, done. If I can prove that no matter where the data is stored on the cluster, it just takes two lookups and we've got the data. Right? That's all they care about. The software engineer will be like, that's great, but if it consumes too much memory, or it's too expensive to run, or it doesn't return the result fast enough, none of those things will work for the software engineer. So all sorts of constraints come in, more practical constraints come in for the software engineer. All right, so here's a great example of this from 2012. IBM shrinks bit size to 12 atoms. So this was 3 years ago now. IBM researchers say they've been able to shrink the number of iron atoms it takes to store a bit of data from about 1 million to 12. Andreas Heinrich, who led the IBM research team on the project for 5 years, said the team used the tip of a scanning tunneling microscope and unconventional anti-ferromagnetism to change the bits from zeros to ones. And this solved a theoretical problem of how few atoms it could take to store just one bit. So we're talking about 8-byte. A byte has 8 bits. They're talking about storing whether it's a 1 or a 0. It's down to 12 atoms now. He says, now comes the engineering challenge, how to make a mass storage device perform the same feat as a scanning tunneling microscope. Right? So it's great that you've got it down to 12 atoms. If I can put this on a USB stick, I could be holding terabytes of data or petabytes of data on that USB stick. But not if we can't make it work, right? Not if we can't solve the engineering problems of putting that into production. So there's a difference between the research theoretical and then the engineering. And they've got people at IBM who work just on this. How do I make this into a mass storage device that we could sell using this technique? All right, so here's another definition. What is engineering? So we just step away from software engineering and just look at engineering. This really it's huge and complicated, but it pulls everything together. So engineering is a sequence of well-defined, precisely stated sound steps which follow a method or apply a technique based on some combination of theoretical results derived from a formal model, empirical adjustments for an unmodeled phenomenon, and rules of thumb based on experience. And this is actually another answer as to why mechanical engineering is so far ahead of us on certain things, is they've had the centuries that it takes to have enough experiments to develop formal models that have then been proven by further experiments to accurately reflect reality. So if we know that we're building a bridge out of this particular type of material, our models will tell us whether it will stand up to winds of 50 miles per hour. Or if we know that the region that the bridge is going to be in can experience winds of up to 100 miles per hour, certain materials can no longer be used. And other class of material has to be brought in. And that's not guesswork. That was years of empirical adjustments for phenomenon. They built a bridge, it'd fall down. Why did it fall down, right? Oh, it was because the wind burst rate was at 100 miles per hour, and there was, it was too much for the materials that were used. And so software engineering is in the baby steps. We're only about 50 years old, 50, 60 years old. And we have to do a bunch of theory work to come up with formal models that can be used. And the problem for us that derails a lot of that work is that in mechanical engineering, the models all touch physics. They all go down to a reality-based mechanism which behaves similarly each time you interact with it. Whereas with us, we throw people in there. And as soon as you throw people in there, all bets are off. So we have to go much slower in developing theories that apply across multiple contexts or multiple techniques because of the fact that we just haven't had enough time to really develop really formal models. So we'd love to be able to say at some point, given a task of this complexity, so we know it's going to involve, there's enough requirements on the table that it's going to require 1,000 people working on it. So given a task of this complexity, a team with an average years of experience of X and a team size of Y will produce the software needed in D years, right? We're nowhere near that in any way, shape, or form. But if we want to become like the other engineering disciplines, we have to get to that. And that's what software engineering research does, is to try to move us. What are some models that are based on mathematics, based on reality, that we can use across contexts? Now, this definition that I just read is independent of purpose, right? So we have mechanical engineering, civil engineering, electrical engineering, software engineering, right? We want to take this approach of well-defined steps, sound steps, precisely related formal models, unmodeled phenomena, adjustments, etc., rules of thumb. Hey, this worked last time, which is the rule of thumb. And apply it to the construction of software systems so that we can get better at what we do. All right, running out of time here. I'm going to skip this one. Actually, no, I won't. I like this one too much. Anything that I don't get to, I'll just spill over to Thursday. So, software engineering is that form of engineering that applies a systematic, disciplined, quantifiable approach and the principles of computer science, design, engineering management, mathematics, psychology, sociology, and other disciplines to creating, developing, operating, maintaining cost-effective, reliably correct, high-quality solutions to software problems. And after writing that sentence, Daniel Berry could retire and go do something else. But that really captures, at a really high level, what software engineering is trying to do. So what are we trying to do? We're trying to create correct, high-quality solutions to software problems that are both cost-effective and reliable. Right? That's what we're trying to accomplish. How are we going to, and we want to make sure that we can do that by creating, developing, operating, and maintaining those things. To draw upon that, we need systematic approaches that say, well, if this is day one and you've done nothing, do this first. And now you've done that, so do this next. We would like to have a systematic approach. We'd like it to be quantifiable so that we're measuring ourselves. And then we can say, how well did we do on this iteration? What can we do better on the next iteration? And then here's where the complexity starts to peek through. He's saying that you need people on your team or in your organization that has expertise from really diverse fields. So yes, you need computer science, but you also need design. That would mean more like product design as opposed to software design. Engineering in general, management, mathematics, psychology, everything. And psychology, sociology comes in because we're dealing with humans. Humans on our teams, humans as users, they will directly impact what our software can do and how effective it can be. All right, and then he threw in that notion of the word discipline here. And this is something, just my own little personal anecdote. When I see that word discipline, what does that mean? Well, that's where we as individuals come in. Are we going to be disciplined about how we apply our knowledge? If I'm in an organization and they say that the software lifecycle that we're following is XYZ, am I following XYZ? Am I contributing to what the organization says we're going to do to make this work? Now, I can contribute to it, and then if I see problems, it's on me to also report, I don't think this is working, can we get to something that's better? But am I following it? If I'm not following it, I'm throwing a monkey wrench into the works, right? So, and then there's got to be a disciplined approach to how I program. So we'll talk about, Agile talks about testing first, as opposed to code first. It's a very hard one to get rid of, but if you become disciplined, you can get yourself there, where you're, before you write the feature, you write the test. That way, because you're never going to write the test after you've written the feature. But if you write it before, then it's already done, and then you can go work on the code, and then the test tells you when you're done. Right? So you get benefits, but you have to be disciplined. And personally, I was always an amateur musician in my life. I was a trombone player. I only ever kind of really practiced when it was band time. I did a little bit of practice outside, but not much. And that was true both at elementary and high school and college. I just used it as a stress relief. I would have fun with it. But I knew that if I wanted to ever step out of amateur status and become professional musician, that I would have to start practicing music with my trombone 8 hours a day. And that was the difference between me and people in college that were professional musicians at the same time, and me as an amateur. I would just practice every now and then. They were practicing 8 hours a day, and they would actually complain if they didn't get their 8 hours to practice in. They go, oh, my chops are all shot to hell. I wasn't able to practice 8 hours yesterday. I'm just like, I couldn't believe it. But then there's just this huge difference in quality in terms of what you see. A professional musician will show up, be ready, have already practiced everything, and if you throw new music at them, they play it perfectly almost the first time. And so you can see that if you do the same investment in coding skills, you're always testing, you're always doing versioning management, you have continuous integration, you know how to break things up into smaller and smaller tasks, you're always estimating how fast you're going to do. it's noticeable when you find someone that's got that built in and someone that isn't. They've got this notion in the industry called super programmers. And super programmers, compared to average programmers, are almost always 10 times more productive, 10 times less errors, 10 times faster at producing stuff. And I've seen 1 or 2 individuals that are easily 100 times faster than other people because of everything they've learned and how efficient they are in the type of work they do. All right, so I didn't get through everything, so I'm going to start here on slide 25 on Thursday. And I'll have a goal of getting through these slides and through the slides. What I want to jump to before I lose all of you, at the very end of this lecture, I say, please read the following paper by Thursday. It's called No Silver Bullet by Fred Brooks. Just log into D2L website. It's there for the download, and read that by Thursday. Thanks.